Now that we have introduced entropy, talked about how it's a property, talked about what it is and the chaos and the disorder, we're now going to get into Chapter 8 for the 10th edition and look at entropy analysis. Here's the objectives. Not going to go through them too much, but you can see we're basically going to apply these in these types of things for steady flow, different flow devices, things like that. Entropy analysis balance. So lots of formulas. You're going to see lots of formulas. That's, I think, why these lectures go through so quickly, because spending time going through all of them doesn't really make a ton of sense. We need to work them, right? So, but just a note, we do have specific formulas for like when kinetic and potential energies are negligible. So just different things that we can use for different situations. And when you're solving these problems, that's why it's really important to know what you have or know what your system is doing so that you can go back and say, oh, but my KE and PE are negligible. So maybe I can use this for my reversible steady flow work. And then the Bernoulli equation, the steady flow of a liquid through a device that involves no work interactions. So just a steady flow of liquid through a device. So here's the reversible steady flow work, and you see this. Reversible work relations for steady flow and closed systems. And just a note, the larger the specific volume, the greater the work produced or consumed by a steady flow device. Of course, because we know, think of it like a waterfall, right? If you have a very small waterfall and you're trying to propel a water mill, you're going to have very little work produced for that. If you had a huge waterfall with an enormous water mill, we're going to have way more work produced, right? So the larger the specific volume, the greater the work produced or consumed, just depending on what you're looking at, by a steady flow device. Okay, and so here's some schematics for the TS diagram. But here's an example, compressing a substance in the liquid versus gas phases. And this walks you through all of this. So this is great to reference. And it also puts it on a TS diagram here. Okay, and even a schematic for you to look at, versus a pump versus compressor, right? Compressing a liquid, you would use a pump. Right? You're pumping, you're compressing that liquid. But you're compressing a vapor, you would use a compressor. Right? So proof that steady flow devices deliver the most and consume the least work when the process is reversible. So taking the heat input and work output positive. So here you have actual reversible denoted here. And then you have the schematic over here of a turbine. So you have P1 and T1 going in, you have P2 and T2 coming out, and then what do we get? We get the work. We get the work out. The reversible work rate. Remember this dot right here is to denote rate. Remember that little dot? It's the rate of something. And of course that's going to be higher than the actual work out. Of course, because it's under idealized conditions, it's going to be the very best. A reversible turbine delivers more work than an irreversible one if both operate under the same end statements. That's going to be the same, right? It's going to be the same of anything. The reversible is always going to outperform because it's under idealized, it's perfect conditions. So here's some, remember we talked about it when kinetic and potential energies are negligible. There's a whole process here. But isentropic, so it's when we're holding it constant, and then you have polytropic when PVN is constant, and then you have isothermal when PV is constant. I think I said in the last one 0. I hope I don't refer to it as 0. I don't mean it's 0. I mean constant when it says isen or iso. Okay. And then the adiabatic compression, PVK, constant, equals constant, requires the maximum work, and the isothermal compression, T is constant, temperature is constant, requires the minimum. Why we have a active slide here. Let's move on over to here because this is really good. On the PV diagram, you have plotted here the isentropic, right? So N is equal to K. The polytropic, 1, N is in the middle of K and 1, so you see it a little bit left. And then isothermal is N is equal to 1. So you have isothermal and then polytropic and then isentropic. And the PV diagrams of isentropic, polytropic, and isothermal compression processes between the same pressure limits. So we're looking at the same pressure limits. We're starting at the same place, but the isentropic, polytropic, and isothermal definitely end up in different places. The multi-stage compression with an intercooling. So the gas is compressed in stages. So it's compressed in stages and cooled in between each state by passing through a heat exchanger called an intercooler. Remember we looked at that tube for the heat exchanger? Let's see. So you have this tube, right? And remember I said, hey, we may have things that we need to cool or heat, but you can't mix them, right? So the gas is compressed at stage and then cooled between each stage by passing through a heat exchanger. So just depending on how the heat exchanger is set up, maybe this is your gas, right? And then this is some kind of like hot liquid, or vice versa. Maybe this is the hot liquid and in here is the gas, but it's separated by this tube, right? And so all of this is around. But you do have some formulas here. And to minimize compression work during two-stage compression, the pressure ratio across each stage of the compressor must be the same. So that there's not so much. And the PV and TS diagrams for a two-stage steady flow compression process. So this is talking about pressure, right? Because it's in pressure stages. You can see that really well here. So you've got pressure 1 going to 2. We've got an intercooling here, and then, pressure 1, and then we're going to an intercooling, and then we're ending up in pressure 2. Right, same here. We've got the first pressure, the first compression, then we go to an intercooling, and then we've got the second compression. So 2 stages, right? So we have 1 and 2 stages of compression. And the same for this, 1 and 2 stages of compression. So here, the more closely the actual process approximates the ideal isentropic process, the better the device performs, of course. The closer we get to an ideal anything, the better the performance. Thus, it would be desirable to have a parameter that expresses quantitatively how efficiently an actual device approximates an ideal one. Therefore, it is more desirable to have a parameter that limits our idealized, that says, hey, this is our limit. This is our ideal limit. This parameter is the isentropic efficiency or adiabatic efficiency, which is the measure of the deviation of the actual process from the corresponding idealized one. Its efficiency. It's going to measure actual to idealized to give you efficiency, and whether it be isentropic or adiabatic. Isentropic efficiencies are defined differently for different devices, since each device is set up to perform different tasks. So it's just saying, hey, you're going to have individual characteristics or individual parameters, depending on what you're doing. The isentropic process involves no irreversibilities and serves as the ideal process for adiabatic devices. How do we know that this is irreversible? How do we know? If this didn't say, if this wasn't here and this wasn't here, how would we know which one is which? This right here. It's saying that there are no irreversibilities, that they are equal. Whatever we're putting in here is here. There's nothing changing. That's how we know that this is the ideal and reversible one versus the actual. Okay. Isentropic efficiency of turbines. So this is just graphed on an HS diagram for an adiabatic turbine. So here, for a turbine under steady operation, the inlet state of the working fluid and the exhaust pressure are fixed. Okay? So we have those fixed, the inlet state of working fluid and the exhaust pressure are fixed. Okay? So this is fixed and this is fixed. And you see that on the red line, P2 and P1. The ideal process of an adiabatic turbine is an isentropic process between the inlet state and the exhaust pressure. Okay? And so you see that green line. It's the ideal. Right here. And you have that efficiency noted here. Here are some more schematics. Not going to get really into them. We're just talking about efficiencies, works. Of course, we know isentropic, right? No irreversibilities present. It's going to be perfect. It's going to look here. Oh, what is it really? Really, it's going to be over here. It's not going to be perfect, right? We're not going to have entropy that does nothing. Right, that stays the same. It's not going to happen. What we're really going to have is, where's my marker? Here it is an increase in entropy. That's what we're really going to have between 1 and 2A. Isentropic efficiencies of compressors and pumps. So we're talking about those efficiencies. Remember, N denotes efficiency. And then again, 2S, right? So this is the entropy. So when you have, just like here, this entropy is equal. Just like here, when you have it equal, that's going to be your isentropic. Isentropic, which means that there's no irreversibilities, which means it's ideal. It's perfect. But then this is actually what's happening. And again, it's increasing in entropy. A realistic model process for compressors that are intentionally cooled during the compression process is the reversible isothermal process. And we have that for an efficiency formula right there. Okay. And then not going to go into that too much because we will actually answer those. And then compressors are sometimes intentionally cooled to minimize the work input. Do you remember when we were going through the heat engines and I said, wow, maybe you could take out some of this work that we're expelling or some of this heat that we're expelling and put it in to help power, right? To reduce some of the work. So maybe we can cool it so that we don't have to put in so much work to be done. Maybe we can make the parameters or the environment for this compressor easier to work. Here's an isentropic efficiencies of steady flow devices continued. And it's really just the T or K S diagram. And again, you don't have entropy increasing. So this is the isentropic, and then this, again, is the actual process. And it just has formulas for efficiencies. So this is the isentropic efficiency of nozzles. So this is the efficiency formula for that. And if the inlet velocity of the fluid is small relative to the exit velocity, then you can use these. The inlet velocity of the fluid is small relative to the exit velocity, then you can use these. And so here we have that again, and you're going to always see this entropy increase on actual processes. And you're going to see this P1 and P2 held as fixed, inlet and exit pressure. Here, same thing again. There's just more formulas that we're going to be working. a substance leaves actual nozzles at a higher temperature, thus a lower velocity as a result of friction. That's because we lose some. We have degradation of the system, right? Due to chaos, due to irreversibilities, the presence of them, such as friction. The entropy balance, so we have mass balance, we have lots of different balance equations. We have one as well for the entropy balance. The entropy change of a system during a process is equal to the net entropy transfer through the system boundary and the entropy generated within the system. So it's very easy, right? Entropy in, less entropy out, plus entropy generated. So the difference plus what we gained by just having a process is the change in entropy of a system. Excuse me. So here is the change in energy of a system, and you have entropy. So here's your system. You have energy coming in, and guess what you've got accompanying it? Of course, entropy. And then you have some energy going out and leaving with it some entropy. Right? But still, entropy generated is going to be zero. It's going to be more chaotic. Entropy change of a system is the delta change, remember, because this is always change. Okay, and we talked about that. Entropy change is equal to entropy at the final state, less entropy at the initial state. So it's just the difference. And you can take the integrals when the properties of the system are not uniform to find the entropy of the system. So you can do that. Mechanisms for entropy transfer, S in and S out. Heat transfer, of course, we talked about that because, well, that's how energy is transferred. Entropy transfer by heat transfer, here's that Q over T. They are pretty simple equations when you start getting into that. Heat transfer is always accompanied by entropy transfer in the amount of Q over T, where T is the boundary temperature, because that's where energy is happening, which means things are happening. And so therefore, chaos is happening. Therefore, we've got entropy being generated. Entropy transferred by work, because we transfer energy two ways, heat and work. No entropy accompanies work as it crosses the system boundary, but entropy may be generated within the system as work is dissipated into a less useful form of energy. So, while it doesn't happen at the boundary, it does happen within it. Okay? And so, therefore, we do denote that as zero. Entropy of work is equal to zero. But it can happen on the inside because the entropy generation via friction. So we still have it because energy is being transferred, right? So when you start talking about energy is not, when we're calculating, it's not happening on this wall, right? So entropy is not transferred with the work. It's a generation via the friction byproduct of it. So where you have it, it will generate, but not so much with it as being accompanied. Does that make sense? So that's why it's zero. Work doesn't accompany, or entropy doesn't exist with the work, but it accompanies it in a generational effect via the friction or other irreversibilities. So the mass flow rate, entropy transfer by mass flow. So you see entropy mass is equal to ms. And you have these formulas. Mass contains entropy as well as energy. And thus mass flow, right there. Mass contains entropy. It contains entropy as well as energy. And thus mass flow into or out of a system is always accompanied by energy and entropy transfer. Entropy generation, so S gen. So you have S in and out. S in and out. Plus S generated. That's the system, and then this is just S in and S out. S generated. And this is of the system. These are just the formulas, but these are mechanisms of energy transfer for a general system. The total entropy generated during a process can be determined by applying the entropy balance to an extended system that includes the system itself and its immediate surroundings, where the external irreversibilities may be occurring. Because remember, the irreversibilities, the friction, the dissipation, things like that, that's where we get and measure entropy. So we want to take into account the immediate surroundings that are going to be impactful. The entropy change in this case is equal to the sum of the entropy change of the system and the entropy change of the immediate surroundings. So it's just saying that we take into account those things. Entropy generation outside the system boundaries can be accounted for by writing an entropy balance on an extended system that includes the system and its immediate surroundings. So it's just talking about how we work in that entropy balance equation. So we do have it for a closed system. The entropy change of a closed system during a process is equal to the sum of the net entropy transferred through the system boundary by heat transfer and the entropy generated within the system boundaries. And so it gives it to you for an adiabatic closed system, as well as a system plus the surroundings that we just talked about. Entropy balance for heat transfer through a wall, because you can definitely put some heat through a wall. It's and these are rates, remember? Rate of entropy in less the rate of entropy out plus the rate that the entropy is generated. And you do have that in Q rate over T in and out as well. So here's the schematic. And where it's set to 0 because we've got a balance, right? So here, entropy generated when a hot block is dropped in the lake. It's just a schematic that we have, but basically it's just taking those formulas and putting it in. So if we have, entropy generated equal to the change of the total entropy is also equal to the change in the entropy system plus the entropy of the lake. That makes sense. It's just all together, right? Entropy generation associated with heat transfer. So this is just taking the same slide as before and just putting it in regard to a heat transfer. Okay, so net energy transfer by heat mass plus the entropy generation is equal to the change in system entropy. Okay, so here's a graphical representation of entropy generated during a heat transfer process through a finite temperature difference. Because remember, when we start talking about finite changes, that some of these we regard with negligible change versus no change, right? So here, the wall is ignored. Here, the wall is considered. So this is, you can think of it, it's very small. Oh, we're just going to ignore it. It's negligible, right? Here, the wall is considered. Well, we know that we'll have a little bit. So we'll consider it. And then here, the wall, as well as the variations of temperature in the system, are considered. So the system and its surroundings, right? Okay, here are the entropy balance for control volumes. So we do have some steady state. We have steady state with a single stream, steady flow, single stream, adiabatic, things like that. This is when you have, something like this, right? A control volume, and you have one inlet, one exit, things like that. Okay, entropy balance for control volumes. The rate of entropy change within the control volume during a process, okay? The rate of entropy change within a control volume during a process is equal to the sum of the rate of entropy transfer through the control volume boundary by heat transfer. The net rate of entropy transfer into the control volume by mass flow, and the rate of entropy generation within the boundaries of the control volume as a result of irreversibilities. And that's carried on. I won't say that's carried by work because S generated by work is 0, but it's coming in form of things like friction. and you have friction when you're talking about works, things spinning, stuff like that. So the entropy generation within the boundaries of the control volume as a result of irreversibilities. The entropy of a substance always increases or remains constant in the case of a reversible process, but basically always increases as it flows through a single stream adiabatic steady flow device. Entropy balance for a throttling process, we've got it here. Here we've got it on a TS diagram, and then you have H constant following this line through that process from state 1 to state 2. But still, pretty easy. We're just talking about rates right here. And so we've got a very simple formula. Entropy, the rate of entropy generated is equal to the mass rate times S2 minus S1. And then entropy generation in a heat exchanger. So you see this heat exchanger. And again, just not too much. What you do is we just take that same formula and we just account for the different states and the different working fluids. So here we've got mass flow rate of the air and then mass flow rate of the steam. So in summary, again, lots of formulas because there's a lot of individual situations that you'll need those for, but you will get those when you actually start working them. Reversible steady flow rate, minimizing the compressor work. Of course, we want to minimize it, and we do that maybe by cooling. Isentropic efficiencies of steady flow devices. In entropy balance, so that's where we can calculate it. We're setting it to 0. Entropy balance for closed systems, and then entropy balance for controlled volumes.